In this slide, we're going to look at the two different methods for representing vectors mathematically. The first method is geometric. And basically, when you're representing a vector geometrically, you're representing it with a picture. And we're going to see how we can draw pictures that represent vectors and how to manipulate those pictures. And you'll be surprised, there's actually quite a lot of information that we can get from these very simple pictures. Secondly, we want to be able to represent vectors algebraically. That means representing them as an equation. Now, in general, these two methods are equivalent, but you're going to have to learn both approaches, and you're going to have to learn how to go from one to the other. You know, if you start with the geometric approach, you'll be able to write an equation. If you're given an equation, you'll be able to draw the appropriate picture. And so these two approaches together give you the complete picture, and we're going to need both. Now, we're going to start with the geometric approach, and in the geometric approach, we represent a vector with an arrow. And so we can see a little arrow here. We've got the tail of the vector and the tip of the vector. And the very end of the tail and the very end of the tip, those are the 2 points of the vector that are the most important. Now, we've talked previously about how a vector has both a magnitude and a direction. And both of these things are represented in our picture. So the length of the vector from there to there, that represents the magnitude. If I drew a longer vector, so here I've got a longer vector, that would represent a vector with a bigger magnitude. So the length of the vector that you draw when you represent it as a picture, that determines the magnitude. Now, the tip of the vector, that determines the direction. So both of these vectors are pointing in the same direction. I could also draw a vector, in some other direction, and I would have the length and the direction both specified by that picture. Now, we just talked about how different lengths of vectors represent different magnitudes. And so you can actually quantify that mathematically by scaling the length of the vectors with a scalar. In other words, let's look at these three vectors at the bottom. We have this vector A, which is pointing to the right, and then I've drawn a vector that's half the length of A. Now, those are directly related. So this is exactly half the length of A, so we would say that's 1/2 the vector A. Now, if I double A, if I make it twice as long, then I have 2A. So what I've got in each of these cases, I've got the vector A, which is multiplied by a scalar. On this topmost vector, there's a 1 that's understood there, so there would be 1 times A. Here I have 1/2 times A, so it's half as long. Here I have 2 times A. It's twice as long. Each of these numbers, 2, 1/2, and 1, those are scalars. And so I've multiplied these vectors by scalars. What that's done is changed its length. Note what hasn't changed, the direction. So only the length is changing here, but we're scaling the length of the vector by multiplying it by a scalar. So what's the takeaway here? Simply, when you multiply a vector by a scalar, it changes its magnitude by that multiplication factor. Now, there's one exception to this idea that multiplying by a scalar doesn't change direction. If you multiply a vector by a minus sign, or that's equivalent to multiplying it by -1, you flip the vector 180 degrees. And so here we have a vector A, and here I have the vector minus A. Now notice these have the same length because the magnitude hasn't changed. I've just multiplied the length by 1, but I've multiplied it by -1, so that changes the direction. Changes it how? Just a 180 degree flip. And this brings up a really, really important point because I emphasized very strongly earlier that when you talk about the magnitude of a vector, you're talking about a positive number. Magnitudes are always positive. So what do the minus signs do? They tell you directions. So this minus sign here tells me the direction is flipped. And we're going to be able to use that to construct a vector that's pointing in any direction in terms of positive and negative numbers. But we'll see how that works when we get to the algebraic approach. Right now, we're still just looking at the pictures, the geometric approach. Now there's a lot of information in this slide, and so let me hit some of these highlights. And I've got these two vectors that I had on the previous slide. I've got my A vector, and then I've got my negative A vector, which is the same length but the opposite direction. Now imagine that I was a person standing someplace and I decided to walk to some other place. I could draw a vector between where I started and where I ended up. And that's actually something called the displacement vector that we're going to learn about later, but it's just basically a vector pointing from where I start to where I end up. And if I go back the other direction, I end up where I started. And so you could imagine me going this way and then going that way. And I end up where I started. And this approach is similar to what we did when we added the two vectors of the force vectors acting on that crate in a previous video. What we're doing is we're adding up these two displacements. The displacement from the starting point, you walk, across the room, and then you walk back. If I add these up together, I end up where I start. So the amount of displacement from where I started would be 0. And what I've done here is I've added the vector A to the vector minus A, and I end up with 0 back where I started. This works for any kind of vector. You could imagine a box where I'm applying a 10-pound force here and a 10-pound force there. They're in equal and opposite directions, so I'm really applying a 10-pound force and a negative 10-pound force. Those two forces are going to cancel out, and that box is not going to slide across the floor. So the result of adding those two vectors together would be 0. And what we've got when we add a negative vector, it's just like adding a negative number to a positive number. You're doing subtraction. And so we're going to talk in more detail about how to do vector subtraction in general, but this is our first example of a vector subtraction. And there are a couple of other key things about this equation that we want to point out. And so I'm looking at this equation here. The first thing that I want to point out is this equal sign, because in math, when you have an equal sign, that's very powerful. It says the stuff on the left of the equation is the same as the stuff on the right of the equation. These things on the left are vectors. A vector minus a vector, these are vectors. So we can't just set it equal to 0 because 0 by itself is a scalar. That means that the 0 that we set it equal to has to be the 0 vector. And we define the 0 vector as a vector of 0 length and some undetermined direction. So it doesn't really have any direction. It could have every direction. It doesn't really matter. But a 0 vector is a vector with no length and no direction, or at least an undetermined direction. Now we're continuing to think about this idea of adding vectors together, and we've seen how to add positive vectors and negative vectors together. Here are a couple of examples. We have a 10-pound force going to the right and a 5-pound force going to the left. Again, this could be our crate that we talked about previously. When you add these two vectors together, what you end up with is a net force with a magnitude of 5 pounds going to the right. I think that probably makes sense to everybody, that the 10-pound force is bigger, so it's going to overwhelm the 5-pound force, and you're going to end up with an effective force of 5 pounds. In other words, if I have my crate here, and it's the same crate, and I have a single 5-pound force pushing to the right, that crate is going to slide to the right. This situation here with the 10-pound and 5-pound forces is completely equivalent to that, because the box is going to slide the same way in this situation as it would in that situation. So the net force is 5 pounds to the right. And let me say again, we're talking about vectors, and vectors have direction. So if I showed you a problem and I said, what's the net force? If you said 5 pounds, you would be only half right, because that to the right is part of that vector. It's its direction. Now, down below, we see another example, one that I just talked about in the previous slide. If I have 10 pounds from the right and 10 pounds, or 10 pounds going to the right and 10 pounds going to the left, those two forces are going to cancel. Now the box may get smushed a little bit, but it's not going to be sliding across the floor because these vectors add together to 0. And another way that we can say that is that the two vectors cancel. Now when we talk about adding vectors up, so far all the vectors that we've looked at adding together have been in a straight line. Either positive or negative direction, but all along the same line. But of course, we know that a vector can point in essentially any direction we want it to. So how do you add two vectors together that aren't lined up along the same line? Well, we're going to use a method that I call the tail to tip twice method. And the basic idea is very simple once you get it down. But in order to do that, I want to make a sort of a definition. If I tell you that I want to add the vector A to the vector B, I'm going to call the vector that's to the left of the plus sign, or it could be a minus sign for subtraction, we're going to call that the first vector, and the one that's after the plus sign or the minus sign, we're going to call that the second vector. And so I'm making those labels so that I can talk about the first vector and the second vector, and you'll be able to see how to arrange them. Now, this is the picture that we're going to end up with when we do the vector addition, and you can see that it forms a triangle. So sometimes this method is called the triangle method, but I actually like to call it the tail to tip twice method because that tells you how to do it. So we're going to consider these two vectors, the A vector and the B vector, and I want to form the sum r equals A plus B. Now, how am I going to do that? The tail to tip twice method says it's a two-step process. So the first step is to connect the tail of the second vector. Which one's the second? The one after the plus sign. So I'm going to connect the tail of B to the tip of the first. Now remember, the tip is where the arrow is, and so I'm going to take B and place it so that it is connected tail to tip. So the tail of the second connected to the tip of the first. A is the first, B is the second. Once you do that, you draw the straight line from the tail of the first to the tip of the second. That's why it's tail to tip twice. So the first tail to tip is the connection, the tail of B connected to the tip of A, and then the second tail to tip is the drawing. You draw from the tail of A to the tip of B. Tail to tip twice. So let's do some examples. I've got three vectors here. I've got a vector C, I've got a vector D, and a vector E. They're different lengths, they're different directions, and I want to form the vector sum C plus D. And so I'm going to do tail to tip twice. And so that means D is my second vector, so I'm going to connect the tail of D to the tip of C. Now, it's worth mentioning something at this point. A vector is defined by its length and its direction. So I'm allowed to take this vector D and scoot it anywhere on the page that I want, as long as I keep the length the same and the direction the same. If I keep those two things the same, the length and the direction, it's the same vector. So I'm going to take my C vector and scoot it down here. I'm going to take my D vector and scoot it there. And now I've got them connected so that the tail of D is connected to the tip of C. That's my first tail to tip. Then I'm going to draw my vector sum. My vector sum goes from the tail of C to the tip of D, and I draw it. Now, one thing that I want to caution you, you have to draw the arrowhead on your sum. If you just drew this red line without the arrowhead, I wouldn't know which way the direction of the sum vector was pointing. In other words, which way does the vector C plus D point? You have to draw the arrowhead in order to specify that. And if you don't do that on a test or a quiz, I'm not going to give you full credit. So make sure you keep that in mind. Let's look at another one. I want to connect D plus E. So again, I'm going to take my E vector. The tail of E is going to connect to the tip of D. So here's my D and E connected tail to tip. And then I draw from the tail of D to the tip of E. And that forms my vector sum, which I've drawn here in red. And that's the vector D plus E. It's that simple. What if you want to add three vectors? Now, that can be a little bit tricky, and there's actually a couple of different ways that you can do it. There's sort of the long, tedious way, and that would be I could form the vector sum of c plus d, and that would be a separate vector c plus d, a new vector, and then I could take c plus d. Here you can see up at the top I've kind of grouped c plus d together. I could take that sum, c plus d, and then add it to e. And so I would basically be doing two different sums. It's a two-step process. But there's a shortcut. If I want to add a bunch of vectors together graphically, I can just keep connecting them tail to tip. And so I've got C and D, the tail of D connected to the tip of C. I just keep adding the next vector is connected to the tip of the previous vector. And then once I've got all my vectors that I'm added up chained together in this tail to tip fashion, I go from the tail of the first to the tip of the last, and that gives me my vector sum. So if I wanted to draw the vector sum c plus d plus e, that's all you have to do it. Now, I want to just point out that this tail to tip twice approach works even if there's not an angle between the vectors. They don't always make a triangle. If they line up, they're going to always be in the same line, so you won't be able to get a triangle, but you still do the same tail to tip twice. So if I wanted to form the sum p plus q, I would be able to simply connect the tail of q to the tip of p, and so we see that's been done right there. And then I draw from the tail of p to the tip of q, and that would be the length of the vector sum. And I've drawn it offset a little bit here so that it doesn't overlap and get confusing, but if you were really drawing it, you might even draw it just on top of the original two vectors. What if I wanted to draw q plus p? Well, I would just reverse the order because the second and the first apply. So I could draw, q and p, so that would be the q vector and that would be the p vector, and then I could draw q plus p, that's p, and that would be the same vector sum. So you just do the tail to tip twice and it'll work every time. Okay, we want to look at another example now. That example is to show that vector addition obeys the commutative property. You might remember the commutative property from some of your math classes. It basically means it doesn't matter what order you add things up in. In other words, we know that regular numbers, scalars, are commutative. If I add together 3 plus 4, I'm going to get the same result if I add together 4 plus 3. It doesn't matter what order I add the numbers in, I get the same answer. Is that true for vectors? If I add two vectors A and B together, do I get the same result regardless of what order I add them in? It turns out, yes, you do. And it's really easy to show that if I have two vectors A and B. So for example, I've got this vector A here and this vector B here, and I've left the arrow off the B vector there, but I've got them connected tail to tip. And so if I draw this blue line here, that's going to be the vector sum A and B, because this is the second vector, this is the first vector, I've got them connected tail to tip. But if instead of starting with A and adding B, if I start with B and go up, and then I add A, I've reversed the order, and I've added B plus A together, but the sum is going to be that same sum. And what's startling about this picture is that you can see that these vectors, A and B, when I add them both ways, A plus B and B plus A, all together it forms a parallelogram. And the vector sum is the diagonal of the parallelogram made by those two vectors. And so we can actually use this fact to have a different technique for adding two vectors graphically. We have the tail to tip twice method, where we can scoot the vectors around and connect them tail to tip and draw tail to tip. But now we can also connect the two vectors tail to tail, See how A and B are connected tail to tail right here? And if I connect them tail to tail, and then I form the parallelogram that they make, the diagonal of that parallelogram is my vector sum. So to summarize, this is how you do it. This is how you add two vectors together using the parallelogram method. So the first thing you do is you connect the tails of the two vectors together. And the other method for addition, you connect tail to tip. Here we're connecting tail to tail. So you connect the tails together. You draw the parallelogram spanned by those two vectors. You just saw how the two vectors connected form a parallelogram. And then you draw the diagonal of the parallelogram. And it's important always to indicate the direction. So the direction of the vector is away from the connection point where those two vectors are connected. So let's see how to do this in an example. We have three vectors here, C, D, and E. I'm going to pick two of them. I'm going to pick C and I'm going to pick E, and I want to add them together. Now, of course, we could do tail to tip twice, but we're going to do this with the parallelogram method. And so what's the rule? So I want to take my two vectors, C and E, and I want to connect them tail to tail. So C and E are connected tail to tail. Now, what I want to do is I want to take my vectors and repeat them. So I've got my C vector, I've repeated it here. I've got my E vector, I've repeated it there, so that I form a parallelogram. And so I can draw the diagonal of my parallelogram, and that's going to be C plus E. That's the way to do it. Now notice, if I look at just up top, C vector, E vector, those two vectors are connected tail to tip. If I go down the middle, I've done just my regular tail to tip method. That gives me C plus E. If instead I go E and C, that would give me the vector E plus C. E plus C and C plus E are equal to each other. We've already seen that. So what you end up with is an assurance that vector addition is indeed commutative, and we can see how to apply it to actually add some vectors together graphically.